Okay, so new topic for today. Last time we were talking about matrices representing linear transformations, and how, in particular, how if you pick bases, you can use a basis to represent an abstract vector as a list of coordinates. You can use bases to represent a linear transformation as a matrix. Okay. So a seemingly unrelated new topic for today. And I say seemingly, it turns out this is actually extremely closely related. It's just in a way that we can't see yet. And we're going to see how that connection works on Wednesday. And it's really a remarkable thing. So anyway, here we go. Eigenvectors and eigenvalues. This is the equation that this section is all about. It happens sometimes. Given a matrix, here, let me use a better color. It happens sometimes, given a matrix, that there might be a vector V with the feature that when you multiply that matrix times that vector, you get a scalar multiple of that original vector. All right, so this happens sometimes. Now, you might look at something like this and think, all right, well, coincidences happen, and so what, right? And that would be a good, a reasonable and understandable point of view to take right now. But again, as I kind of hinted before, it turns out this is actually really important. Why it's important, again, we'll start to see the beginnings of that on Wednesday. Ultimately, why we're really going to care, the big applications that we're going to care about of that in this course are going to come around largely in Chapter 6. Believe it or not, this little phenomenon of a vector multiplying by a matrix to give you a scalar multiple of that vector, this is going to allow us to solve some differential equations. It's weird. It's kind of hard to see it coming, but this is going to be a key concept there. Okay, so lingo, the vector. This vector is called an eigenvector, and the value here is called the eigenvalue. So it's just that's just terminology. All right, now a couple of observations I'll make. First, notice that the input vector and the output, after you multiply by the matrix, is a scalar multiple of it, and of course, a scalar multiple of a vector has the same number of coordinates as that vector, right? So this matrix multiplies by a vector of one dimension, you might say, and gives a vector of the same dimension, and therefore this matrix is square. So we can only talk about eigenvectors and eigenvalues of square matrices. So going forward for the rest of this chapter, every matrix is square. Another observation I'll make, this equation always works if V is the zero vector, and so that means that if you consider the case of V being the zero vector, it's just not interesting. It doesn't tell you anything special about the matrix that you can multiply it by the zero vector to get the zero vector. It's not worth making a thing out of it, right? So when we say eigenvector, in order to keep that reference notable, to be worth something, we're going to exclude zero from the terminology. So when we talk about eigenvectors, one of our requirements and assumptions is the eigenvector is not zero. Okay. Okie dokie. Now, just a little bit of more lingo. We're not going to do anything with this in this course, but so think of this as kind of a cultural reference. There are other kinds of analogous things that happen, not with matrix times vector, but with some linear transformation acting on some vector in a vector space. Right? We've seen lots of examples of vectors in vector spaces that are not Rn, and linear transformations that themselves are not, matrices. So when something like this happens, but in the case where you're talking about a linear transformation instead of a matrix, we still kind of use the eigen prefix. So and I'm going to go into any details of these examples, but there are certain kinds of functions that are solutions to certain kinds of differential equations that you can view as being relevant to an equation like this one above, and we call such functions eigenfunctions. And it just means It's an eigenvector of the equation that looks just like that one up there, just applied to a linear transformation. So analogous. So likewise, when you're doing quantum mechanics, a quantum state, right, that describes a state that a particle can be in, can be thought of as, weirdly, a vector in a kind of a vector space, and there is a very natural linear transformation that you can apply to it, and as such, quantum states that satisfy a rule like that, again, big surprise, we use the same linguistic construction, they're called Eigenstates, right? So, anytime you see the prefix eigen, what it means is you're talking about a thing that satisfies an equation kind of like that in some sense. Okay. All right. So, again, this is our big equation. Next question. How do you compute these things? In other words, given a matrix, how do you find the eigenvalues? How do you find the eigenvectors? And it turns out there's a very reasonable algorithmic process to do this. Here again is that equation that we're going to try to solve here. How do you find the eigenvectors? How do you find the eigenvalues? First observation I'll make, I can stick in the identity matrix in here for free. And then I can take this term and move it over to the other side, and the punchline is that equation is equivalent to this equation. Now, okay, who cares? Right? What does this buy for us? Well, notice that there is something interesting about this equation here. This equation, you see, we have a non-zero vector that's in the null space of a matrix. Now, hold up. How can you have a non-zero vector in a null space of a matrix? Well, it means that the matrix has got to be singular. Right? I'll refer you back to all of the stuff that we did in chapters 1 and 2. You remember the very last page of the lecture notes on linear algebra, the first part of the linear algebra in section 2.4, I guess it was a list of like 15 or 16 equivalent conditions that are all equivalent to a matrix being singular, or by their negatives, non-singular. So this is one of them. If you have a non-zero vector in a null space, the matrix has to be singular. Okay. So how does this help us? Well, singular matrices have this feature. And what's nice about this feature is that it's something that's pretty algebraically computable. Right? So that's going to be our big idea. The way we're going to find eigenvalues is we're going to look for roots of this characteristic polynomial, they call it. Thus, therefore, giving us eigenvalues, thus giving us values that would make this matrix singular, and therefore, for which we know there exists an eigenvector. That's the strategy. We'll do a bunch of examples in a couple of minutes. By the way, once you know the eigenvalues, finding the eigenvectors is easy. The eigenvector, you can see right here, it's just going to be any vector that's in the null space of A minus lambda I. Right, so eigenvalue first by looking at the characteristic polynomial, and then eigenvectors by taking the corresponding null space. Okay. Okie dokie, let's get our hands dirty and actually do one. Here we go. Here's a matrix. Let's ask what are the eigenvalues and eigenvectors for this matrix. We're going to follow the procedure on the previous page. Step 1, I'm going to take this matrix, I'm going to subtract lambda I. Now, neat observation, this is a kind of a quickie time saver. Notice that matrix that I started with, you can see it right there, and subtracting lambda I, well, I is just ones on the diagonal, so subtracting lambda times I means you're just going to subtract lambda off the diagonal entries. That's the convenient little shortcut observation. Right, so characteristic polynomial is that determinant. So we need to compute the determinant here. The determinant's a matter of multiplying it out. Now, a little bit of algebra. Multiply it out, collect terms, factor. y'all know how to do that stuff. I'm going to let y'all fill in those blanks. But note that with the fully factored characteristic polynomial, fully factored characteristic polynomial, it's pretty immediate to infer the roots. And per the discussion on the previous page, the roots of the characteristic polynomial are the eigenvalues of the original matrix. So we're, depending on how you look at it, sort of halfway done. We found the eigenvalues. These are the two eigenvalues. Quick pause. How are we doing? Any questions? Everybody good? Yep.
Could you explain again how you put in all those values into the determinant matrix?
I'm sorry, I don't understand.
Could you explain how you figured out what values would go in each element of the matrix?
Oh, you're wondering where this matrix came from? Yeah, it's just A minus lambda I. So the A matrix, you can see the four elements of the A matrix right here. Right, that's this A. And lambda I mean, I is the identity. It's all zeros but with ones on the diagonal. So lambda I is going to be all zeros but lambda on the diagonal. And so subtracting lambda I means you're just subtracting lambda off the diagonal. Is that what you were looking for? Yeah. Cool. Okay. Right. Okay, so reminder. Eigenvalues, right? These eigenvalues here are roots of the characteristic polynomial. And then having found the eigenvalues, having found the eigenvalues, the way we're going to get the eigenvectors is we're going to look for null space vectors of A minus lambda I. Now, I do want to give you all one little quick warning here. The common mistake that students make is they then look for vectors that are in the null space of A. And it's an easy sort of oops, right? Because you've got these matrices that you're messing with. A was a matrix that was given to you originally, and we've argued that, you can see right here, eigenvectors are null space vectors. Look, E equals 0, right? But it's easy to forget that specifically they're null space vectors not of A, right? But of this other matrix A minus lambda I. So heads up, it's a common landmine to step on. Don't forget that eigenvectors of A are null space vectors of A minus lambda I, not vice versa. Okay. All right. Okie dokie. So let's do that. And again, it's just a matter of writing it all down. Here's a for example. Let's look at this eigenvalue right here. Our first eigenvalue, you might say, right? Take that eigenvalue, plug it in, and A minus lambda I turns into that. Reminder, here's our formula for A minus lambda I. Right, we're just subtracting lambda off the diagonal from the original matrix. So, having done that, the null space equation that I'm looking at is this one. And I got to find all these null space vectors, homogeneous solutions if you prefer. And so I'm going to say, yada, 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 right? Chapter 1. Row reduce, solve your pivot variables in terms of your free variables, all that business. And here's your set of solutions. So I encourage you all to go through this process. Make sure that you remember how to do row reductions. I know it was a long time ago, right? But it's part of the process. Okay. And so, by the way, now we're actually kind of done with the first part of the problem. For this eigenvalue, we have found this eigenvector. You can take this and plug it back into the original equation. Let's go ahead and do that just for convenience. Let's see. So -1 and 3, 2. Okay, so up here, let's take, better color. Three, 2, right? Let's ask the question, do we get here, as argued, eigenvalue -1 times 3, 2? And it's just a matter of doing the arithmetic. But yep, sure enough, works out. So, again, what that means is that this vector here is the eigenvector, is an eigenvector, and this value here is the corresponding eigenvalue. Okay. All right, now I want to show you all a shortcut that will save you some effort. Specifically, I want to show you a shortcut around this business, the whole, row reduce, solve your pivot variables in terms of your free variables, all that business. It can be a little tedious. In this case, it's not bad. It's really easy to row reduce this matrix, but nevertheless, still, here's an even better solution, an even better way to find this vector. I should say these vectors. Come back and talk about that in a moment. So here's the idea. It's going to seem to be a digression, but in looking at this equation, instead of going straight at the solution, let me ask this semi-related question. What's the rank of that matrix? Now, who cares, right? Okay, but nevertheless, humor me. What's the rank of this matrix? Here's the thing about it. This matrix, the rank can't be 2. Now, how do I know that rank can't be 2? Well, because, look, it's A minus lambda I. I already know lambda is an eigenvalue. And the whole point of A minus lambda I, the whole point of switching to this version is because this matrix will be singular. And again, long list of equivalent conditions back in chapter 2, but a matrix being singular means that the rank cannot be in this case 2. So I know the rank of this matrix is not 2. Okay, fine. What about zero? Maybe the rank of this matrix is 0. Well, no, obviously not. I mean, if the rank were 0, that means there's no pivots. That means there's no first non-zero entry in any row. That means there's no non-zero entries. It means the whole matrix would be 0. That matrix is obviously not all zeros, right? So it's an immediate throwaway. So it can't be 2. It can't be 0. It's got to be 1. Right? So by process of elimination, easy observations, process of elimination, the rank of this matrix is 1. Now again, who cares, right? How does it? We're looking for solutions, not abstract discussions of things that we're not immediately interested in. Okay. But bear with me. If the rank is 1, then I can compute the dimension of the null space. The dimension of the null space is n minus the dimension of the column space, aka the rank, and so the dimension of the null space is also 1. It's 2 minus 1. Okay, now with getting closer to relevant, right? We're trying to find the null space. By knowing the rank, I can compute at least the dimension of the null space. It still remains. I'm looking for the null space itself. But we're actually really close at this point. The fact that the null space is one-dimensional ends up being crazy useful. And it goes like this. We're looking for a vector space that's one-dimensional. One-dimensional vector spaces are really easy to understand. You just find any vector in that vector space other than 0. Again, silly, right? Well, any non-zero vector in that vector space, and you've got yourself a basis, and you have therefore found the whole vector space, right? So the beautiful thing about this situation, then let me zoom out where we can see the whole thing. Here again is our question. We're trying to find all of these null space vectors. This argument here says that because the null space is one-dimensional, I could just find any solution and declare it a basis, look at all of its multiples, that's all the solutions. So can we find any solution here? Can I think of any vector that when I multiply by that matrix I get 0? And then just get into sort of smart alecky mode and you notice, okay, well I see 2s and 3s and, okay, well, 3, 2. right? Just play that trick where you just switch the numbers and change the minus sign, and of course it's 0. Right? So there's a really nice punchline to this argument then, right? So argue that the dimension of the null space is 1. Casual observation of any solution. Declare victory. Simply look at all multiples. Okay, now, so you say, frankly, this looks like an entire page of work, and I think I'll just go ahead and do the row reduction, right? Right, the row reduction is a lot less, it seems. Well, yeah, but what I wrote here is for communication purposes, right? This is your first time to see the argument. I wanted to expand it out dramatically. You don't have to do this in practice. Let me show you with the next one what you can do in practice. So here's for the next eigenvalue. Remember, we had 2 eigenvalues. So for this next eigenvalue, here's what a minus lambda I turns into. Again, we need to find a null space. Now, instead of row reducing, here's what you can do instead. You can say rank equals 1 implies dimension of the null space equals 1. And then just write down your answer. And I think this is a perfectly satisfactory explanation. The rank is 1, right? It follows that the dimension of the null space we're looking for is 1. And it really is obvious that 1 comma negative 1 works. I mean, that's just simple arithmetic. That part's obvious. The fact that our null space we're looking for is 1-dimensional, therefore makes it obvious that all the solutions are just all multiples of that. So I think this is a lot less to write down than even a relatively easy row reduction, which, by the way, would involve fractions, right? All the more undesirable. So for your consideration. I want to encourage y'all to make arguments. Keep in mind this is the compact version, but this argument as here that I've got expanded, I want to encourage y'all to find these null spaces of eigenvectors by this quicker method. Okay. All right. Oh, why am I erasing that? That was good. Let's leave that there. Okay. So let me point out something about language coming back over to here. This first example we were looking at, and we're going to see several more examples. Bear with me. So we looking at this matrix, we found 2 eigenvalues. And looking at that first eigenvalue, we found for that eigenvalue infinitely many eigenvectors. Okay. So here's the thing. Of course we found infinitely many eigenvectors. It's always infinitely many eigenvectors. That matrix A minus lambda I is always singular. That means that the null space is always going to be at least 1-dimensional. That means that the number of eigenvectors is always going to be at least infinity. Right? So it just becomes a little bit cumbersome to say, to the question, how many eigenvectors did you find? To say, well, I found infinitely many, of course, but more relevantly, I found that the collection of eigenvectors is a vector space for which there is a basis consisting of 1 eigenvector. Right? So it just gets old. Right? You would say that over and over again, and it's always infinitely, but... Okay, so that's just not how people talk. And when you're talking about eigenvectors and how many eigenvectors you found, it is understood and highly standard to simply say, I found 1 eigenvector. By which it is always understood to mean that, well, you found 1 linearly independent eigenvector, or you found a basis for the vector space of eigenvectors. The basis consists of 1 vector, right? But it's just a lot easier to say, I found 1 eigenvector, as opposed to, and of course, all linear combinations, or and of course, all multiples of it. So anyway, heads up about the terminology. I'm going to be doing that a lot here in this course, and again, it's very standard, so you got to be on the lookout for that. So if someone says, hey, I found 2 eigenvectors, well, what they mean is they found a vector space of eigenvectors where 2 of them were linearly independent, or said differently, they have a 2-dimensional vector space of eigenvectors. Okay. All right. So with that in mind, let's look back over here. This summary of the what we came up with. We started with a 2x2 matrix. We wrote down the characteristic polynomial. It was a degree 2 characteristic polynomial. We found 2 roots, aka eigenvalues. And with the lingo in mind, we found, as a result, 2 eigenvectors. Right, 1 eigenvector for the first eigenvalue, 1 eigenvector for the second eigenvalue. Total of 2. Okay, so now notice the pattern. 2s everywhere. Right? And now I want to draw an analogy. Think back to chapter 4 when we were solving nth order constant coefficient linear differential equations. Right? Y'all remember all that chapter 4 business? And let me just remind you that if you have an nth order equation, then you get a degree n characteristic polynomial, which will have n roots, counting multiplicities, right? And which therefore gives rise to n solutions. So you think back to that, and you think to this, and it's like, oh wow, look, 2, 2, 2, 2, 2, just like in chapter 4, it was n. Hey, maybe there's something analogous going on here, right? Wouldn't it be nice? It's kind of, based on this first example, I would say expected, sort of, that a 2x2 matrix, wouldn't we kind of want to presume that you would always get 2 eigenvectors? And you can probably tell from my intonations, it just doesn't happen. And the analogy is just poor. Imperfect. Anyway, the analogy is imperfect. And I'm going to show you an easy special case. Here's a matrix. Now, it's 2x2. Naively, you might expect there to be 2 eigenvectors. Well, let's play the game. Here's the characteristic polynomial. There's 1 root. Okay, now asterisk. Yes, I see there's 1 root, but that root does have multiplicity 2, right? So if you count multiplicities, there are kind of 2 roots. But looking for the eigenvectors, well, you got to take this eigenvalue. That is, multiplicity or not, that is our only eigenvalue. Here's the eigenvector equation then. Yada, 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 however you like. Rank argument, row reduction, whatever. There is only 1 eigenvector. And that's the end of the story. So now back in chapter 4, we were looking at a certain kind of solutions. We were looking at exponentials, and sure, when there's a multiplicity, the exponential solution isn't always the only. But then there's these hidden solutions. X times an exponential, x squared times the exponential. There's all those additional solutions that we found later. There's a temptation to think, oh, well, maybe there's more eigenvectors and we just haven't found them yet. But that's not the case. It's a sad story. This is it. There's only the 1 eigenvector. There's 2 eigenvalues in some sense, again, counting multiplicities, but there's only 1 eigenvector. So, again, the analogy's poor. Just be aware of that. Don't presume that you will always get what I will loosely call the expected number of eigenvectors. Okay. Another example. Let's do a 3x3 example here, just to get one under our belt. There's a matrix. Characteristic polynomial. Now, I just yada, 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 a lot of algebra. Right? So, you got to fill in those blanks. But there's your characteristic polynomial. Quick aside, you'll notice here that this is not a minus lambda I. This is the negative of a minus lambda I. So question, why lambda I minus a? instead of a minus lambda I. First of all, I want to point out it doesn't really make any difference. We're looking for roots of the determinant. Right? So the determinant of these two matrices may differ by as much as a minus sign, but they're going to have exactly the same roots. They're going to give you exactly the same eigenvalues, therefore. So why one versus the other? Well, some people like the fact that this one over here on the right is easier to write down because you just subtract lambda on the diagonals, and that's kind of nice. Right? On the other hand, some people like the fact that lambda I minus a, written like this, when you compute its determinant, will always have a leading coefficient that's 1. That's kind of nice. A minus lambda I here, if you were to take the determinant of a minus lambda I, the leading coefficient would be -1. And so anyway, it doesn't matter. Take your pick. You're up to you, your preference. But you'll see both in different circumstances. Okay. So either way, here's our characteristic polynomial, easy roots. Go through and play the game, starting with this first eigenvalue. The eigenvector equation is this. And play the game. Now, so again, if you want to row reduce, you can. Feel free. Go ahead. Feel free to row reduce. I'd rather make a rank argument. Let's do the rank argument for this matrix. Let's ask first, what is the rank of this matrix? Now go through the list of possibilities. Could it be that this matrix has rank 3? No, of course not. It's a minus lambda I. It can't have rank 3. That would make it non-singular. This matrix has to be singular. So 3, not possible. Also, 0, not possible, right? The rank can't be 0. So it's not 3, it's not 0. So all that remains is 1 or 2 as a possible rank. Now, how you distinguish between 1 or 2 as the possible rank, you've got options on how to do that. I'll point out that let's look at the column vectors. These two column vectors over here, the right two column vectors, are obviously not multiples of each other. So the column space is clearly two-dimensional. Right? It can't be one-dimensional. If the column space were one-dimensional, these would have to be multiples of each other. They're obviously not. So, therefore, the rank has to be 2. And if the rank is 2, let's see here. The rank is 2. In fact, let me, okay. So the dimension of the column space is 2, so the rank is 2, and that means that the dimension of the null space is 3 minus 1, 3 minus 2, sorry, 3 minus 2, and therefore 1. All right, the in is 3. The rank is 2, so therefore the dimension of the null space is 1. We're looking for a one-dimensional null space. That means I just need to find any null space vector. Can I think of any vector that multiplies by this to give you 0? Yeah, sure. How about that one? Again, smart alecky observation. Notice that column of zeros on the left. So 1, 0, 0 works, and therefore is a basis for my null space. And there we go. So there you go. So again, didn't have to do a row reduction. Let me pause on that one. A little bit different from the examples we've done before. Is everybody on board? Happy? Okay. Right. So that was for this eigenvalue here. Now let's look at the next one. Let's look at -1. For lambda equals -1, a minus lambda I is that. Again, we've got a null space to think about. Here, and how am I going to find the rank of this matrix? Well, I think it's pretty easy to observe that the row space. Again, this one just happens to be set up a little bit differently. That's the way the cookie crumbled. Here, the row space is pretty clearly one-dimensional. So that means that the rank is 1. That means the dimension of the null space is 2. And the dimension of the null space being 2, I have a little bit more work that I have to do. I have to find a couple of vectors that are independent. But these zeros make life pretty good, right? All I really have to do is find vectors that dot well with that one row, right? And pretty easy to notice that 1, 3, 0 works. Pretty easy to observe that negative 1, 0, 1 works. And depending on your preferences of arithmetic convenience, I'm sure you could dream up other vectors that obviously would work. Right? But we only need 2. We just need 2 that are independent. We have found 2 that are independent, and therefore we're done. This is the entire null space, again using that rank argument. Let me pause there for a second. Everybody okay? Yep.
So you basically guess
Kinda. Yeah, I mean, certainly that's where I got these vectors from. I was just, and a guess isn't really quite right. I mean, I wasn't exactly guessing. It's not like I was coming up with numbers randomly. It's more like, think about how you could be smart alecky Weisenheimer, right? So I see the 3 and the negative 1, and I think, hey, how about I multiply this one by 1, this one by 3, right? And then, let's see, how else can I conveniently get these numbers to add up to 0, right? Well, okay, so I see the 3 and the 3. I put 1 here and a negative 1 there. So you're looking for easy foot in the door. Yeah, right, yes.
Do you also have, for example, 0, 3, 1?
Yep, totally. That would work just fine as well, right? So that would give you a different basis, right? If you chose the vector you said and this vector, let's say, then that's a different basis for that same two-dimensional vector space. But if you're thinking about, hey, what about this vector and the vector that you came up with? Well, that is 3 vectors. We know that our null space is two-dimensional. That means that of those 3 vectors, now there's a relation between them, and you can't just declare those 3 to be a basis. There's too many. So now exactly what that relation is, I don't care. Doesn't matter, right? The point is, you just need any 2, and so I can pick these 2, or you can pick your 2, and it's fine.
So you can choose whatever 2 of those 3 and you get.
Yep. All good. Yep. Anybody else? Okay. All right. Right. Yeah. So, quick summary. Eigenvalues are roots of the characteristic polynomial computed like so. Eigenvectors are vectors in the null space of A minus lambda I. Again, don't accidentally find null space vectors for A itself. That's not the same. Right? Again, it's a common landmine for students to step on. So, heads up. Okay. All right. Another little bit of lingo that we have to get said. The word Eigen Space is it's just the vector space consisting of all the eigenvectors for a given eigenvalue. So it is that null space. It's all the eigenvectors. Specifically, that's the eigenspace for a given eigenvalue that we write as a subscript. So we'll use this notation a lot. E sub lambda is just the vector space of all eigenvectors for that eigenvalue. Quick asterisk, I did throw away as eigenvectors 0. Right? Remember, so 0 is not allowed to be an eigenvector. So when I say that E lambda is the vector space of all eigenvectors, I should say it's the vector space of all eigenvectors and 0. Right? You got to put the 0 back in there because 0 is not an eigenvector. Okay. So a quick observation. And by the way, remember the vector space of eigenvector, the eigenspace, right? We talk about how many vectors are in that eigenspace with this kind of math slang, right? We won't say, well, of course, there's infinitely many vectors in the eigenspace. No, we talk about the number of eigenvectors as how many vectors are in a basis for the eigenspace. Namely, what's the dimension? So by this little formula right here, dimension of the eigenspace, the way you should read this is how many eigenvectors for that eigenvalue, lambda. So this little theorem here says two things. It says that for any eigenvalue, so if lambda is an eigenvalue, you will always have at least one eigenvector. That's the first half of this statement. That's easy to prove. I'm going to leave that as an exercise for you all to think through. Think about how you'd go about doing that. It's an easy observation about, well, look, if lambda is an eigenvalue, then a minus lambda I is singular. Just remind yourself what it means for a minus lambda I to be singular. That has consequences, and this is one of those consequences. So if you have any questions about that, good question to ask in discussion section or in my office hours or whatever. So the second statement that we get out of this is that the number of eigenvectors will never be more than the multiplicity. That's not easy to prove. That's actually pretty hard to prove. So don't try to prove that fact. We're going to use this in this course. It's a big deal that the maximum number of eigenvectors is the multiplicity, but we're not going to prove it at any point. Now, that said, I am going to make another statement in section 5.5 about something called Jordan canonical form, and if you look at Jordan canonical form the right way, then a consequence of Jordan canonical form could be viewed as that the number of eigenvectors is never more than m. But I'm not going to prove that theorem about Jordan canonical form either, right? So in fact, we are never going to prove this result here. It's just beyond the scope of Math 216. Okay, so good fact to know. Nice consequence of that is that if you want to think about what's the total, the most eigenvectors possible, keep in mind this dimension here is the number of eigenvectors for that first eigenvalue. If you were to count up all the eigenvectors that you get for each one of the eigenvalues, grand total, all of the eigenvectors together, what's the most you could possibly have? Well, best case scenario, the number of eigenvectors for a given eigenvalue is the multiplicity. That's the best case scenario. Those multiplicities, of course, add up to n. So, therefore, the most that you can possibly have, maximum possible number of eigenvectors, is n. If you have an n by n matrix, n is the maximum number of eigenvectors you could have. Okay, so that's another thing that we're going to, I would say, make big use of, but mostly I'll say that this is something that we're going to come to regret when we start solving differential equations, and I'll talk about why when we get to chapter 6. Okay. I want to draw some pictures. Now, again, we've already talked about how what an eigenvector is. It's a vector that when you multiply by the matrix, you get a scalar multiple. So here we go. Let's look at this matrix there. Recognize we've already found the eigenvectors and eigenvalues for that matrix. There's an eigenvalue and eigenvector. Here's an eigenvalue, eigenvector. Now let's draw a picture. So this vector here, 3, 2, has the feature that when you multiply by this matrix, what does A do? What happens to this vector when you multiply by A? Well, you're just multiplying the vector by, let's see, how am I going to do this? You're just multiplying the vector by minus 1. Right, so the matrix multiplies that vector by minus 1 to give you that vector. Let me say that a little bit differently now. Don't forget, when I say this is an eigenvector, really I mean that and all of its multiples are all eigenvectors. So everything on this entire line has the feature that when you multiply by this matrix, you just flip over to the other side of the line. It's just everything on this green line gets multiplied by -1. So said differently, it's really easy to understand what the linear transformation does on that line. And then analogously, let's look at this vector, 1, -1. There it is. That vector and all of its multiples, right, have an analogous feature, and that is that when you multiply by the matrix, you're just effectively multiplying by 4, right? So everything on this line gets stretched by a factor of 4, and in this, for the case of that first vector, gets turned into that. Right? So in some sense, knowing the eigenvectors and eigenvalues, it gives you a geometric point of view on what the matrix is doing in the plane. Whether this is your favorite geometric point of view on what the transformation is doing, maybe, maybe not. But it's giving you a couple of lines on which the linear transformation is easy. On this green line, you're just multiplying by -1. On this blue line, you're just multiplying by 4. So, for example, if you want to talk about, let's say some vector like this one. Let me do a better job of this vector here. That's a sum of a green vector and a blue vector. Right, red is equal to green plus blue in this case. Well, what does the matrix do to this red vector? Well, the green part is going to get multiplied by -1. The blue part's going to get multiplied by 4. Oh, come on, straight line. Right, and so grand total then, the red vector goes to about there. Right, so to whatever extent the red vector points in the green direction, it's getting flipped by -1. To whatever extent the red vector points in the blue direction, it's getting multiplied by 4, and that adds up to this. So anyway, it's a point of view, a kind of a geometric point of view. This next example is highly analogous. This is just one dimension up. Recall we talked about this matrix. We found eigenvalue, eigenvector, eigenvalue, couple of eigenvectors. So that eigenvector means that everything on that line gets multiplied by 2. Right? And this tells us that let's say it this way, these two vectors, furthermore, every multiple of those two vectors, or in fact even better than that, every linear combination of those two vectors just gets multiplied by -1. So this linear transformation here on R3, in the E1 direction, right, everything gets stretched by a factor of 2, and in this green plane, everything just gets multiplied by -1. And everything else is a linear combination of those. Okay. Alrighty. Last observation. Oh yeah, we've got a couple of minutes. That clock's fast. Okay, so we're good. We're good. I'll be real quick with this one. This matrix here, you'll recall that this is a rotation pi/2 counterclockwise. We talked about rotation matrices not too long ago. And first, a quick appeal. A rotation, if you think about it, how could a non-zero vector, when you rotate this vector, how could you get a multiple of the original vector? Right? A rotation seems like you're going to get a different direction than you had initially. How could you possibly get a scalar multiple of what you had before? So there's a temptation to look at this and say, there's no eigenvectors at all. And we already know that when we've seen an example, algebraically anyway, of a matrix where there was a shortage, I'll say a disappointment of too few eigenvectors, fewer eigenvectors than we were hoping for. So is that what's going on here? And I want to point out that no, it's not. This is not a shortage of eigenvectors. This is just a sort of a little bit too naive interpretation of this matrix. That is only a rotation if you restrict your attention to real vectors. If you allow consideration of complex vectors, there are eigenvectors just fine and dandy. Here's your characteristic polynomial. It totally has roots. No problem. Those are the eigenvalues. Right? And for a given one of the eigenvalues, I mean, go through and play the game, a minus lambda I and all that, and row reduce, etc. And there's an eigenvector. So this matrix does have eigenvalues and eigenvectors. It's just that they're complex, not real. Okay. So likewise for the other eigenvector and eigenvalue, the quick theorem I want to end with is straight out of the book. If you have a real matrix, and if you have an eigenvalue and eigenvectors, then the conjugate is also an eigenvalue, and the conjugates of those initial eigenvectors are also eigenvectors. So it works really, really nicely. This is not hard to prove. It's kind of a matter of writing it down and observing that, well, yeah, sure enough, that works. So eigenvalues and eigenvectors can be complex. Okay, we're out of time. See y'all later. Have a good Monday.